Here at the MIT Nuclear Reactor Lab, we have fission reactions going on in our core, and that means that there are uranium-235 atoms that are splitting into neutrons, heat energy, and other smaller atoms. Power reactors use the heat energy to generate electricity, but it turns out that there's so much more that you can do with a fission reactor, like measuring tiny amounts of a bunch of different elements. We can even measure arsenic in a sample of hair.
To do this, I take my hair sample, place it in this container, put the lid on, and put it in this tube here. From here,
the hair gets sent through the pipes into a chamber that's right next to the reactor core, where it absorbs some neutrons, which makes some of the arsenic in the hair radioactive.
After 12 hours in the reactor and a few days of decay, I take the sample, put it in this lead container to protect me from the radiation, and I go analyze it. I put the hair sample in this detector, which is very sensitive. So sensitive, it measures radiation from individual arsenic atoms in my hair. The area under this peak tells us how much arsenic is in the sample.
So our reactor can tell us if someone's been exposed to things like arsenic just by analyzing their hair. It
can measure very small amounts of a lot of different elements in materials that are difficult to measure otherwise.
Cool thing number 2 is that
we're using the neutron beam produced in our reactor to see the microscopic structure of materials. The neutrons produced by the fission reaction come out as a beam and they hit the sample, which is positioned right here.
When the neutron beam hits the sample acts like a mirror, reflecting the neutrons in all different directions. Inside this drum, there's a detector that measures the different directions and number of neutrons reflected in each direction. And this
can actually tell us how the atoms are positioned inside our sample.
So on the x-axis here is the angle of the detector with respect to the sample, and on the y-axis is the number of neutrons that the detector sees. So at this position, there are a lot of neutrons, almost 1,400 per second. And over here, there are about 600. Down here, there are almost no neutrons. So using these numbers, we can figure out how atoms are arranged inside of a material.
Scientists at other reactors want to use this method to see how the atomic structure of different nuclear fuels change while they're used in a reactor. Seeing these changes can help us develop new, safer, and more efficient types of nuclear fuel. And
using neutrons is the only way that we can see these changes in atomic structure. You wouldn't be able to see the same thing with a regular microscope or any other method.
Number 3, we can turn gold
into tools to fight cancer.
We start by loading tiny seeds of gold into a holder that we call a rabbit.
So I'll take the rabbit over to one of our shielded work areas where we can insert the rabbit into the reactor. And now I'm going to send the gold seeds next to the reactor core.
They go in there, where they'll absorb neutrons and become radioactive. After they stay in there for a few minutes, we send them back out and package them up. We package them up and move the gold seeds into a lead container. The gold seeds are now radioactive, and
the fact that it's radioactive is actually a good thing because doctors are going to take those gold seeds and inject them into a tumor, and it's the radiation from the gold that's going to kill those cancer cells.
Number 4.
Another cool thing our reactor does is we help create electronic components for things like airplanes, train stations, and hybrid cars. So right now, this silicon does not conduct electricity, but I can change that by loading it into the reactor. Okay, so what's happening behind me is that silicon piece that I just loaded is traveling through a tube that runs underneath the reactor core. Once it's under the reactor core, it gets bombarded with neutrons from the fission process. Some of the silicon atoms absorb a neutron and transform into phosphorus. It's this phosphorus that makes the material a really good semiconductor.
This is what the silicon looks like before it goes into the reactor, and this is what goes into electronics. The reactor turns the silicon into a semiconductor in a super precise and controlled way,
which I control from over here. That's why we use these semiconductors in mission-critical components like the power grid and not your cell phone.
And last but not least,
we test materials that can make safer and better reactors in the future.
This morning we put an experiment into our reactor with a special type of salt. So our reactor, like almost all reactors in the world, uses water to cool it. The special thing about this salt is that it can run at much higher temperature than water and still be a liquid. It doesn't boil. So a reactor using salt as coolant instead of water can go to much higher temperature.
And the efficiency of a reactor gets better the hotter it runs. And because there's no water, there's no steam, which means you don't need to have
Thicker walls and bigger pipes to keep the reactor safe. So the salt in our experiment is down in the reactor core. And this experiment is going to let us take that salt, heat it up to the same temperatures that it would be inside the core of a full-size salt reactor, and then hit it with the same kind of radiation that it would see in the core of a salt reactor. And as you hit the salt with radiation, does it produce different products that come out of the salt, or does it change the salt in certain ways? This salt experiment is going to be in our reactor for about 1,000 hours. But that's not the only thing we study. We also look at different materials, fuels, and even sensors to go inside the core of reactors. All of this research is working towards making reactors safer and more efficient in the future.